All right, folks. So let's start with this one, which was what, number 4, I think, on the problems. Okay. And sorry, I'm a little. Want to make sure we get through these. So we got a bicyclist, and they're riding their bike at this speed, and how much work is done by the brakes to bring the bike and rider to a stop? And what is the magnitude of the braking force the bicycle comes to rest in this? All right. So we have our bar graph. What types of energy are going to be involved in this problem? Kinetic energy, good. Maybe some thermal, right? That would definitely, and that would be done by the work external. Any other type?
Potential gravity.
Well, are they going up a hill or down a hill?
It just says that she's like at a complete.
I think it says level. Does it?
It says she rides.
Yeah. So I'm going to assume that they're level. Right? Is that okay? So would we change the gravitational potential? No. Any springs here? Any elastic stuff? No. So I think all we have is kinetic energy and then work that's done and then we're going to end up with some thermal energy, which we don't really put on our chart because it's not a mechanical form of energy. It's a thermodynamic form of energy. So at the beginning, we've got a bunch of kinetic energy. What about at the end? Okay. How do we know that she still has potential kinetic energy at the end? I couldn't hear you. She does? Where does it say that she bounces up and down? Oh, okay. I don't think there is one about bouncing up and down, but that's okay. Well, let's see. At the end it says, bring the bike and rider to a stop. So what about being at a stop means that you have kinetic energy?
You don't have kinetic energy. You're at a stop.
Oh. Well, you have potential if your position changes. If you're in a different position. Did she go up or down? So her gravitational potential didn't change. Did she maybe put energy into a spring?
It's thermal energy, right? With the brakes, no?
Yeah, but that's not mechanical energy. Right, because the only type of energy we have is kinetic that we said in this one. So if there's no kinetic, at the end there's no energy. So where did all this energy go? The thermal. Right, because the brake's using friction, it's that external work. So you have this. Because remember, my initial plus my external work has to equal my final. That's the only way for that. Yes. So, and this is where sometimes people tell me, well, the bar graphs don't help me. Well, how do you get your equation? Because I get it from, there it is, KE plus my negative work external equals 0. So my KE must equal my work external. Substitute in. from my equation sheet. I think they're asking me for my external work, right? Yeah. 1/2. What's the mass in this case? The two of them combined, right? 65 plus 9.8. Kilograms.
Now 65 is 1 for yours.
I'm assuming.
Yes.
And I'm going to get a value for that. And I get 9,570 joules. One thing to be careful of, you look, what units do they suggest? Kilojoules. So I would put in my answer not as 9,570 joules, but 9.57 kilojoules. Or go and change the unit that they suggest to joules. Right? And then the second part, braking force. Well, I'm going to go back to my handy-dandy equation sheet and look and say, oh, force, work equals force times displacement. Oh, I know my work. I bet I don't know my forces. That's what they asked me to solve for. And I know my distance, 6.5 meters. Yeah.
That was way higher.
I got an arrow, but
I know that area.
Daniel got an error too. I don't know what an error means. What do you mean you got an error? Like you went to type it in, the computer just said error? All right, let's go on to number 5.
is that the 6.101?
6.101, yep.
Ah,
It's the Mr. Santos problem. Hopefully he got it correct. Player passes a basketball down the court. Pass breaks the ball, leaves the player's hand with the speed of this, and slows down to this at its highest point. Oh. So, what types of energies are we going to have in this basketball pass?
potential.
What type of potential?
Gravitational.
Gravitational potential. What else?
Kinetic.
Kinetic. Any potential spring energy?
No.
Any external work, you think? I would probably guess no. You know, there's nothing like, they don't say there's air resistance or a bird doesn't come along and grab it halfway through or something like that. So, you know, not a bad idea. Never a bad idea. You know, draw a little sketch. So I'm picturing the ball is going like that, and we're looking at its initial point, let's call that I here, and its final point here. Oops, that final point should have been actually right on here, right here. All right?
That's where it stops.
Nope.
That's not where it stops, right? That's where it stops, going higher.
Right. That's where it turns around. And what do we know you have to do to turn around?
Stop.
You gotta stop. So, when it's released at that initial point, does it have kinetic energy?
Yes.
How do we know? I agree. How do we know?
Two problems.
Because it's moving. Yep.
Yay, I thought you made that.
So I'm going to give it some kinetic energy. Does it have gravitational potential energy when it starts?
Well, very
Oh.
little.
Which one? No or very little?
Very little. Possibly.
It's kind of up to us a little bit, right?
Where do you decide where zero's at?
That's the key here. That's good. That's what I was getting at. Where do we want to put 0?
The point.
Okay. So we're going to put 0,
So it has a low bit. Yeah, it has potential.
so it has some gravitational potential. I'm going to just go with a different color, just make my graph pretty. We'll give it just a little bit there. We said no external work. When it gets up to the top here, to that F point, does it have kinetic energy?
Yeah. No, it stops, right?
Well,
It
let's
still has
see.
some.
It still has some because it says it just slows down. It stopped vertically, but it's still moving
Okay.
horizontally. So, does it have as much kinetic energy as it had before?
I said the kinetic potential is like. So like, it has less kinetic energy. It has like 2 blocks.
Okay. You can switch them. I'm going to bring mine down to here. Because it hasn't completely like stopped or. What's happened to gravitational potential?
It goes up.
It's gone up. But now, my initial plus my work, which is 0, has to equal my final. So I got to make sure this lines up. Let's see how many boxes I have over here. 1, 2, 3, 4, 5, 6, 7, and 2, which is 9. I got 1, 2, 3, 4 here. So I better go 5 here. 1, 2, 3, 4, 5. That way I've got 9 on each side, right? And now what do they want to know? How high above the release point is the ball when it's at its maximum height? Alright. So, let's see. Oh, this gives me my equation, right?
Yeah.
KE before, or we should maybe put I there. We're at point I. Plus P grav at I equals KE final plus P grav final. Right? So, huh? I did 9 on the other side, yeah. I think I'm going to group a little bit here. I'm going to say, I'm going to put all my KEs on one side, and all my PEs on the other side. Hey, what's final minus initial? You guys remember? Something like the top of our equation sheet. Change, right? So really on this side I have the change in potential energy. What's initial minus final? Nothing. I still have my kinetic energies over here. So now I'm going to use my handy dandy equation sheet, substitute in. And here, mg, and since it's change in potential, I'm going to have change in height rather than just height. Is there any way I can simplify that? Can I do anything to simplify it?
I mean, you can take
Yeah.
the end still. 1/2 or no.
Well, I could. Let's do that. Oops. That was supposed to be a V. Can I simplify it any more?
Yeah, take it.
I get rid of the m's, right? And I want to get h by itself. So I'm going to rewrite this as v initial squared minus v final squared over 2g equals delta h. Where do you think that 2 came from? I put them both on the bottom. Santos, you can't sleep during your own problem, man. And now I know all these things. Let's see. My initial was 8.6 meters per second. My final was 7.0. What planet does Santos play basketball on?
Earth.
Hopefully. Let's see what we get. Somebody still has my calculator.
I sure do. You didn't have to add me when it's back.
Alright, here we go, folks. So, the last one we're going to do, we only have a few minutes left in class. In fact, before we get too far, so number 6. I'm going to go kind of fast.
Are you gonna post it?
Yeah. So we've got airplane starts at rest on the airport runway. Excuse me. And it climbs to cruising altitude and maintains a constant speed at that altitude. Notice that our answer, they're looking for units of megajoules. Mega stands for million times 10 to the 6 joules. So
Wait, Mr. Cochran?
I really can't because we're up against the thing. No energy at the beginning. Lots of work done. Goes to the kinetic energy and the potential energy. Of the plane. So all of the work that we're looking for is going to be equivalent to how much kinetic energy and how much gravitational potential energy the plane has at the top. So there's my equation right from my graph. Looking for the external work, because the external work is what caused the change in the mechanical energy. Use my equations: 1/2 speed squared plus mgh. I have everything. It's now plug it in. Hopefully I did my calculator correctly. So my mass for me, 1865. My speed at the top, 2,520. And I'm going to move all that over. The height. Oh, I messed up. My height is 2520. My speed is 99.5. Yep. And I'm going to get a really big number. Yep, I do. Right now, I'm in joules.
Your calculator is back on the table.
That's mega. So I get 5.53 times 10 to the 7th joules, which would be 5.53 or 55.3 megajoules. That's a big one.